By the end of this video, I want you to be able to describe the electron configurations for the atoms of any element using orbital notation, electron configuration notation, and, when appropriate, noble gas notation. Elements of the third period. After the outer octet is filled in neon, the next electron enters the s sublevel in the n is equal to 3 main energy level. Thus, atoms of sodium, Na, have the configuration 1s2, 2s2, 2p6, 3s1. Compare the configuration of a sodium atom with that of an atom of neon back on table 4-3 on page 110 of your text. Notice that the first 10 electrons in a sodium atom have the same configuration as a neon atom, 1s2, 2s2, 2p6. In fact, the first 10 electrons in an atom of each of the third period elements have the same configuration as neon. This similarity allows us to use a shorthand notation for the electron configurations of third period elements. Noble gas notation. Neon is a member of the group 18 elements. The group 18 elements, helium, neon, argon, krypton, xenon, and radon, are called the noble gases. To simplify sodium's notation, the symbol for neon enclosed in square brackets is used to represent the complete neon configuration. Brackets around Ne, the symbol for neon, is equal to 1s2, 2s2, 2p6. This allows us to write sodium's electron configuration as Ne 3s1, which is called sodium's noble gas notation. On page 111 of your text, table 4-4 shows the noble gas notation for the electron configuration of each of the third period elements. The last element in the third period is argon, which is a noble gas. As in neon, the highest occupied energy level of argon has an octet of electrons. Ne, again representing neon, 3s2, 3p6. In fact, each noble gas other than helium has an electron octet in its highest energy level. A noble gas configuration is an outer main energy level fully occupied, in most cases, by 8 electrons. Elements of the fourth period. The electron configurations of atoms in the fourth period elements are shown in table 4-5. The period begins by filling the 4s orbital, the empty orbital of lowest energy. Thus, the first element in the fourth period is potassium, K, which has an electron configuration of argon, 4s1. The next element is calcium, Ca, which has the electron configuration argon, 4s2. With the 4s sublevel filled, the 4p and 3d sublevels are the next available vacant orbitals. Figure 4-19 on page 110 shows the 3d sublevel is lower in energy than the 4p sublevel. Therefore, the 5 3d orbitals are next to be filled. A total of 10 electrons can occupy the 3d orbitals. These are filled successively in the 10 elements for scandium, atomic number 21, to zinc, atomic number 30. Scandium has an electron configuration of argon 3d1 4s2. Titanium has a configuration of argon 3d2 4s2, and vanadium V has the configuration argon 3d3 4s2. Up to this point, 3 electrons with the same spin have been added to 3 separate d orbitals, as required by Hund's rule. Surprisingly, chromium Cr has the electron configuration argon 3d5 4s1. Not only did the added electron go into the 4th 3d orbital, but an electron also moved from the 4s orbital into the 5th 3d orbital, leaving the 4s orbital with a single electron. Chromium's electron configuration is contrary to what is expected according to the Aufbau principle. However, in reality, Argon 3d5 4s1 configuration is of lower energy than an argon 3d4 4s2 configuration. For chromium, having 6 outer orbitals with unpaired electrons is a more stable arrangement than having 4 unpaired electrons in the 3d orbitals and forcing 2 electrons to pair up in the 4s orbital. On the other hand, tungsten, W, which is in the same group as chromium, having 4 electrons in the 5d orbitals and 2 electrons paired in the 6s orbital, is the most stable arrangement. Unfortunately, there is no simple explanations for the derivations from the ideal order given in figure 4-19. Manganese, Mn, has the electron configuration argon 3d5 4s2. The added electron goes into the 4s orbital, completely filling its orbital while leaving the 3d orbitals still half filled. Beginning with the next element, electrons continue to pair in the d orbitals. Thus, iron, Fe, has the configuration argon 3d6 4s2. Cobalt, Co, has the configuration argon 3d7 4s2. And nickel, Ni, has the configuration argon 3d8 4s2. Next is copper, Cu, in which an electron moves from the 4s orbital to pair with the electron in the 5th 3d orbital, and the result is an electron configuration of argon 3d10 4s1, the lowest energy configuration for copper. In atoms of zinc, Zn, the 4s sublevel is filled to give the electron configuration argon 3d10 4s2. In atoms of the next 6 elements, electrons add one by one to the 3 4p orbitals. According to Hund's rule, 1 electron is added to each of the 3 4p orbitals before electrons are paired in any 4p orbital. Elements of the 5th period. In the 18 elements of the 5th period, sublevels fill in a similar manner as in elements of the 4th period. However, they start at the 5s orbital instead of the 4s. Successive electrons are added first to the 5s orbital, then to the 4d orbitals, and finally to the 5p orbitals. This can be seen in table 4-6 on page 114. There are occasional derivations in the predicted configurations here also. The derivations differ from those of the 4th period elements, but in each case, the preferred configuration has the lowest possible energy. Right now, I hope that you can describe the electron configurations for the atoms of any element using orbital notation, electron configuration notation, and, when appropriate, noble gas notation.